let's talk about a classic, a real classic in the world of computer science. You've got a collection of data you need to store. So what do you reach for? An array or a linked list? Now, on the surface, they might seem kind of similar, but how they work under the hood leads to this massive performance showdown. Today, we're going to settle the score.
And hey, if you've ever felt like this Reddit user, trust me, you are so not alone. Linked lists can be seriously confusing. I mean, arrays are simple. They're just neat rows of stuff. But linked lists? Suddenly you're dealing with pointers and nodes and this whole different way of thinking about how your data is actually connected.
So you gotta ask, right? If there's such a headache, why bother? Why are linked lists this absolute cornerstone of programming, the thing that always comes up at interviews? Well, it turns out that all that complexity, it's hiding a pretty awesome superpower. The entire story, the whole showdown between arrays and linked lists, every single advantage and disadvantage, it all boils down to one simple but really profound difference: how they organize information in your computer's memory. That's it. It's a battle of order versus chaos. And this visualizes it perfectly. Think of an array like a perfectly organized bookshelf. Every book is sitting right next to the other in a single neat block. A linked list, though, that's way more like a scavenger hunt. Each item just tells you where to find the next one, but those items could be scattered completely randomly all over the room. So here's the crucial thing to get. An array's magic comes from its predictability. If you know where the shelf starts, and you know each book is, say, 3 inches wide, you can instantly calculate exactly where the 100th book is. A linked list doesn't work that way. Each element, or node, has to hold a little note, a pointer, that literally says, okay, the next piece of the puzzle is over there. So we've got order versus chaos. But how does this difference in memory actually play out when the rubber meets the road? You know, in terms of actual speed. This is where the trade-offs get really, really clear, and you start to see why each one has its own place to shine.
And boom, round 1 goes to the array. Big time. We're talking about accessing an element. You see this theta of one thing? Don't let the fancy symbol scare you. It just means constant time. Basically, it's instant. Getting the 5th element takes the exact same tiny amount of time as getting the 5 millionth element. It's a direct jump, thanks to that neat memory layout.
A linked list, on the other hand, can't do that jump. To find an element, you have to start at the very first node and follow the chain of pointers, one by one by one. It's like being on a train. If you want to get to the 50th station, well, you've got to chug right through the first 49 to get there. That's theta of n for you. It gets slower the bigger your list gets. So, case closed, right? Arrays for the win when it comes to finding stuff. But what if that perfect, beautiful, rigid order? What if that's actually the array's greatest weakness? And here we go, round 2. This is where the linked list lands a massive counterpunch: insertion and deletion. If you want to add or remove an item at the beginning of a linked list, it's unbelievably fast. Constant time again. You just create your new piece and adjust a couple of pointers. But an array? Oh man. To add an element to the front, you have to physically shove every single other element down by one spot. That is a huge, slow operation for big arrays. Now, if the story ended there, it'd be a pretty simple trade-off. But wait, there's a twist. There's this other crucial factor that modern computer hardware brings into the mix, and it gives one of these structures a surprising, almost unfair advantage in the real world. It's called cache locality. So, get this, your computer's main memory is actually kind of slow. To speed things up, the processor has its own tiny, lightning-fast stash of memory right next to it, called a cache. And it's smart. When it goes to grab a piece of data, it doesn't just grab that one little piece, it grabs a whole chunk of its neighbors too, assuming you're probably going to need them next. And this analogy from Geeks for Geeks is just perfect for explaining it. An array's elements are all lined up right next to each other. The CPU loves this. When it grabs the first element, it often gets the next several loaded into its super fast cache for free. But a linked list's nodes, they're scattered all over the place. So for almost every single node, the CPU has to make that slow trip back to main memory. It's a huge practical difference. Okay, so linked lists can be slow to travel through, but we know they're incredibly flexible. So where does this flexibility actually pay off? Well, it turns out you use them every single day, probably without even realizing it. Ever hit the back button in your web browser? That's your browser history. Basically a chain where each web page points to the one you were on before. Classic links list.
What about undo and redo in a document? Every action is a link in a chain. Music playlists, flipping through photos in a gallery. Anytime you need efficient next and previous operations, a linked list is often the quiet hero making it all work seamlessly.
So after weighing all these pros and cons, the performance hits, the flexibility, how do you actually decide? When you're sitting down to write some code, which one is the right tool for the job? At the end of the day, the final verdict really comes down to this. If you need to access elements by their position quickly and your collection of data is mostly a fixed size, an array is almost always your winner. It's fast, and that cache friendliness is a massive bonus. But if you're going to be constantly adding and removing elements, especially from the ends, and you need that structure to grow and shrink on the fly, the flexibility of a linked list is simply unbeatable. And this really gets to one of the most important principles in all of computer science. There is no magic bullet. The goal isn't to declare one data structure better than another. It's about understanding these trade-offs so deeply that you can look at the specific problem you're trying to solve and just know which tool is the right one to pull out of the toolbox. And that kind of leaves us with one last big thought to chew on. As our computer hardware gets more and more complex, how might these fundamental trade-offs start to shift? Will the raw brute force speed of cache-friendly access always win out over the elegant, dynamic nature of flexibility? It's a question that's going to keep defining how we build smart, efficient software for years to come.